come to the front rows. And I promise you, if you don't, you miss some fun, okay? So really, it's up to you. Okay, so most of you will miss the fun. Okay, so I brought with you something to show you magnetic fields. I'm not sure how much the previous speaker showed you, but there's a kind of iron liquid inside here. So please be a little bit careful, because if that gets over the glass, the thing gets transparent immediately and no one else sees things. So be a little bit careful. I have a very strong magnet. So again, it's really strong. Keep away from laptop, mobiles, or peacemakers. So, and I demonstrate to the first row, and you behind have to see later. So if you plug it in, you can beautifully see the field lines. And you can. Molecules of the. Yes, that's a ferroid suspension. It's basically a modern version that you can pull on the magnetic field over. And the molecules are aligned. Yes. Following the field lines. Okay. So you can give it through and have a look, but be careful not to bring the liquid to the front, so no one else will see it. Yeah. And if you just want to see funny movies, just go on YouTube and Google for magnetic liquid. There are people who make fantastic movies out of that by using electromagnets and putting sound on that and things like that. So it's really nice to see, and I hope you enjoy. So I will talk about magnetic fields on very large scales. So galaxy clusters, sometimes a little bit down to galaxies, but mostly galaxy clusters and beyond. And there will be several lectures on different aspects. So this kind of diagram here shows why magnetic fields make life really complicated, because there are a lot of processes running on. So in cosmology, you start from some initial perturbations, which you can observe by for example, satellites like Planck. You have to follow structure formation, which at a certain point means also you have to include star formation, feedback, and a lot of other processes. On the same time, you have to worry about magnetic fields. So it can be either some primordial field, which just get modified by the structure formation, but it can also be something which is more directly related to star formation, to AGN feedback, or things like that. And then all that operates basically via turbulence, so via motions. And you have a lot of crosstalk between them. So magnetic field will modify your diffusion, your transport of stuff, might give you an additional pressure term. On the other hand, all these structure formation processes give you additional motions, give you additional velocity field, which again compresses and amplifies magnetic fields. In all these processes, you have to worry about, if you do it from simulation point of view, about your numerics. There's a lot of things like numerical dissipations, like your resolution and things like that. And then, when you at the end want to observe magnetic fields, there are some more or less direct probes, like with Faraday rotations, and where you can more or less directly measure the magnetic field. But if the magnetic field gets light up by relativistic particles, so that you observe radio emission, then you have also to worry about where these relativistic particles are coming from. And again, they are very complicated processes, either regarded to shocks or to turbulence, which both have big question marks on the details of the plasma physics which is going on. So if you then want to interpret whatever you see in radio, it's far more complicated. So that is just a kind of overview for you to see what is going on. So today, I just want to speak about a little bit on how to measure magnetic fields, so magnetic fields and Faraday rotation, and of course a little bit on radio emission in galaxy clusters, and for that also it covers already a little bit of turbulence and other things which are ongoing in the galaxy cluster. So to make it a little bit more interesting for you and also a little bit more entertaining, I will show you some historical, some basic results, which I think also might be quite interesting. And once a while, I plug in this. You might have noticed that on the first slides there was a cow and there was a magnet. So during the talk, I will also tell you what is the relation between cows and magnets. And I apologize for the guys from Sydney, which might have heard that already, but for the rest, I think that should be quite fancy. And then I want to go through Faraday rotation measurement of individual clusters and tell you a little bit what we learned from magnetic fields from these kind of measurements. And then I will discuss a little bit the different kinds of diffuse radio emissions you see in galaxy cluster and what we learned from that. And again, at the end, the summary will be closely tied to our cows, which likes magnetic fields. So, what is a galaxy cluster? A galaxy cluster is a collection of many, many galaxies, up to thousands galaxies are bound in one potential. And just to show you one very nice optical image where you can see a galaxy cluster, so all these yellowish, reddish galaxies are members of the galaxy cluster. And you also see some gravitational lensing features, which means elongated galaxies from behind the cluster, which are where the light is bended by the total potential of this galaxy cluster. So, why are galaxy clusters so interesting? Galaxy clusters have several very interesting properties. First of all, they are the largest bound and relaxed objects in the universe, which makes them very interesting for cosmology, because if you could measure everything which is in a galaxy cluster, you measure basically the raw composition of the universe. They have sizes of several megaparsecs. They are believed to be at least partially turbulent. The intercluster medium's total mass is up to sometimes even several times 10 to the 15 solar masses, dominated by dark matter. And as I said, they have almost cosmological baryon fraction within that region. So basically, whatever the universe is composed out, you should find it in the cluster. The temperature of the intercluster medium is 10 to the 8 Kelvin, which makes it visible in X-ray via thermal Bremsstrahlung. And the interesting thing about clusters also is that they appear to be virialized, which means they are in an equilibrium, meaning that the velocity you see of the galaxies reflecting the potential corresponds to the total mass, so they are in equilibrium. And also, if you look at the temperature, it also corresponds to that potential. So more or less, things are in equilibrium. Also, of course, during the formation, things can be also quite violent. Thanks. So here's a kind of nice visualization. So if you want to understand how galaxy clusters form, you plug in initial conditions reflecting what you observe on the CMB. You let time evolve, and under self-gravity, you form the cosmic web. And at the junction points of the cosmic web, you form these galaxy clusters, which also shows you already immediately that it's numerically also very challenging. If you want to simulate or investigate galaxy clusters with high resolution, you still have to follow a very large volume of the universe, and typically that is then done by some called zoom technique, where the rest of the universe is resampled with much lower resolution than the galaxy cluster. And again, some typical numbers. Sound velocity is of order a little bit larger than 1,000 kilometers a second. The velocity dispersion up to 1,000. Turbulent velocities are typically 300 of order of, and affine velocity is typically something like hundreds. So, and as it is quite early in the morning, I thought I'd give you a very nice movie, how a galaxy cluster forms. Okay, so there should be also music coming. Yeah, it comes. So I hope it's loud enough, and one of the quiz might be at the end of the lecture, or do you recognize where this movie, from which cinema movie that sound is coming from? So what you see here is something like a several megaparsec large box at very high redshift. Visualized here is the gas from blue to more lighter colors in reflecting the temperature. And additional, there are all the star particles which form in the simulation, which gives you this kind of white dot, and every white dot corresponds to a galaxy. And that here is a zoom in on one of the centers of the two clusters, which at the end of the movie will merge. So you can see how these filaments are forming, how at the knots of the filaments larger structures are forming. You also see already how violent inside the cluster these merging processes are. You see here the atmosphere of the protocluster here gets heated by the shocks driven by all these merging processes. And you see how the shock is making its way through the larger scale structures. You see up there is the second cluster, which at the end will merge. And you can see how these structures falling in are dragging the ICM, are imposing velocities, are imposing turbulence. You see that sometimes these galaxies are merging quite fast through, and through all the evolution, you fly once around the structure, so that is giving you this overall rotation. You can also see that this kind of cosmological web also is not just filamentary, it's also sheets. So now you're seeing exactly a longer sheet, so all the filaments you saw before end up projecting in a very large filament, which means that it's always in one plane. And now if you look, you can also see how the gas of these infalling galaxies gets stripped and mixed into the ICM. You can see that you have this kind of rising bubbles, which at a certain point will fall back because that's a stripped gas. Red is hot, yes. Blue is cold. Yeah, more or less, so 100,000 maybe. And hot means really 10 to the 8-ish. Now you can see that although the two clusters are still distinguished objects here, already the outer parts of the atmospheres are overlapping, and also you would still see two clear clusters. The whole structure already started to and you can already imagine that the magnetic field inside these kind of structures will be very much linked to the dynamics of the structures, because it will be frozen in, it will be dragged around, it will be turbulently amplified. And now at the very end, when the cluster is almost merged, the two cores of the two clusters will pass each other and initiate a very strong shock wave, which you will see as a jumping feature going out. And it's jumping just because the interpolation used to make the movie, of course, cannot capture things which are going supersonically. So when you then see the shock wave, which should be coming very soon, you will see, now you start to see the shock wave here propagating. And these kind of shock waves are, for example, then thought to be related to this, what is called radio relics, which I will capture later in the lectures. But you can nicely see how this kind of gigantic shock waves is propagating through the intercluster medium. Yes. No, we are a local group, so we are a group, not a cluster. So there the temperature will be much less. So now you have several observations you can use to study the galaxy cluster. As I said, first the intercluster medium appears bright in X-rays, in thermal Bremsstrahlung. So you can measure the pressure support, but if you look at details, you might also be able to investigate turbulence, viscosity, and shocks. You have galaxies inside the cluster. So here's an optical image. You see all the galaxies in the Coma cluster. And there are some radio galaxies as well, some of them associated to the cluster. And again, you can, in the galaxies, see the interaction with the ICM. You can also look at how galaxies might seed the ICM with magnetic fields. And if you look in radio, you have synchrotron emission. So again, that's the same Coma cluster here in a synchrotron map. And you can study how magnetic field is evolving and builds up. And you also get clues on how particles get accelerated in these environments. Now, again, just to be a little bit entertaining, here's some very historical remarks on galaxy clusters. So the first observation of or interpretation of a galaxy cluster, also at that time, the concept of extragalactic galaxies was not even born, was by Max Wolf, which in 1901 observed what he called nebulae, or what was that then called nebulae, towards this constellation, which we today know is the Coma galaxy cluster. And what he noticed is that there are a huge overdensity of this nebulae towards a certain direction. And again, here he made a very beautiful map where he just counted the amount of nebulae he sees. And from the density, he gave a gray color. And then he painted this beautiful picture. And again, you can see the Coma cluster. And if you remember the pictures from before, you can even see that the morphology is quite similar. And he was writing here that there are numerous small nebula standing so close together that he was even frightened. So at that time, papers were written in a very nice language. So I wish we would do that these days as well. And the even better thing is that he wrote in this paper that to understand this behavior is very important for understanding the universe. And again, that's all sentences you would put in any kind of proposal today. And that was, again, in 1901, where even the concept of this nebula being extragalactic galaxies was not born. It was still thought that these are part of the Milky Way, okay? But still, it's quite nice to see this kind of text. Now, a little bit later, of course, pioneering work by Zwicky, which measured the velocity of galaxies, already concluded that to have these velocities of the galaxies bound to one structure, you need much more material, much more mass than which is seen in these galaxies. So it was a question of what is this invisible mass to be? And interesting, there was a detection of the diffuse radio source, which today we call the radio halo of Coma cluster. And you could do some very simplified arguments. And that was the first proof then that this invisible material there, which keeps the galaxies together, cannot be the baryons in the diffuse medium, because at that time it was still discussed it could be the baryons in the diffuse medium. Later then, the diffuse X-ray emission from the ICM was reported by the first X-ray experiments, and then some Faraday rotation measurement were done, and magnetic fields were discovered in the ICM. And already in the very early work here, people looked at many more galaxy clusters than the Coma cluster and didn't find any diffuse radio halo in them. So that already basically triggered the big quest. So why some of these galaxy clusters show radio emission and why others do not? And has it to do with the magnetic field, or is it something related to the cosmic rays? And all these things will be touched later in the lectures. Now, here's a X-ray image of a cool core cluster. So that is the central part of a galaxy cluster where you have very high gas density, you have very high surface brightness, and the cooling time of the gas is quite short. So if you calculate formally how long the gas takes to cool, it's much shorter than the time of the universe. So the big question is why we don't see that gas, the end product of that cool gas. And one of the answers to that is that there are these radio galaxies inside the center of clusters, and these radio galaxies get fed by this cooling process, and they drive very gigantic lobes of tens to hundreds of kiloparsec or even larger into the ICM and heat it. And beside of heating that cool core, these lobes have also the nice properties that the surface of this lobe is emitting polarized emission, where you can then map Faraday rotation against the lobes, so you get some information on the medium between the lobe and you. And if you look in other cores of cool core clusters, you can find even several of these old lobes. So this process happens more and more regularly, and if you model the cluster and you model the observations, you have to take that into account. And again, there's a big question how this kind of lobes within buoyant Levises are surviving and not get shredded. And again, magnetic fields and transport coefficients, mixing and suppression of instabilities play a major role. So if you want to understand all these processes, again, magnetic fields are one of the key players. Another feature you see in galaxy clusters are the so-called cold fronts. So that again is a surface brightness image of a galaxy cluster, and you see this kind of very sharp feature here. And there's a more dense part of the cluster is sloshing inside the larger cluster, causing this kind of fronts. But if you look in detail on the fronts, they are really extremely sharp. And if you ask the question, how much thermal conduction you can allow to keep that front such sharp, and how much would it broaden, you come up again that you need magnetic field to strongly suppress Spitzer-like thermal conduction along these fronts, because otherwise they could not stay so sharp. So again, magnetic fields here are important to understand the details. That are, again, observations of two galaxy clusters. So that is, again, our best friend, the Coma cluster. That's a kind of pseudo-pressure map. So if you take the X-ray observations, you get temperature and you can density, and you can make a map of the internal pressure. And you can see the fluctuations here in the internal pressure, and you can interpret these fluctuations in terms of turbulence. And for that work, for example, Schück et al. In 2004 concluded that there's roughly 10% of the thermal energy in turbulence. That is a zoom on the central part of the Fornax cluster. This is a temperature map, so you see the center of the galaxy cluster, but you also see two galaxies here which are moving inside the ICM, and you can clearly see the tail, for example, in this galaxy, where the gas from the galaxy is stripped and left behind. And again, if you want to understand the mixing, the instabilities, and the stripping, magnetic fields are quite important for all these processes. Now, as I said, you also can observe galaxy clusters in radio. So nowadays, we have a handful of galaxy clusters observed as diffuse sources in radio. So these are all brought to the same scale. So that's roughly megaparsec or even 1.5 megaparsec in diameter diffuse emission, which means that they are relativistic electrons which have high enough energies to produce synchrotron radiation inside the magnetic fields. There are a couple of other objects like that. And there are also this object where you have this kind of peripheral radio emission like here, that are the so-called radio relics. And again, the most common interpretation is that they are related to the shocks you saw in the movie before, and that here particles get either accelerated or maybe pre-processed gets re-accelerated to produce this radio emission. And again, so to speak, it's crucial to understand a little bit more about magnetic field before you can interpret these observations. So here again, kind of two examples of this radio relic phenomena. So again, color map here is X-rays, or here's a contour sign X-rays. and the black here is in radio, and here the yellow contours are radio. And you can again see that you have a galaxy clusters which are quite elongated, so there is something merging going on, very disturbed, and you have the radio relics. Sometimes you have this double relics, in some clusters you find only single relics. And again, the big question is how you can relate this kind of ICM physics with the shocks to this emission, which means that you have to couple via some acceleration mechanism, and you have to, again, have the proper magnetic field. Now, in general, what we are left for magnetic field is with a lot of questions. What is its strength, its structure, its origin, how it evolves? Is there a common origin for the magnetic field we see in the large-scale structure? Is the magnetic field we see in galaxies or in groups or in clusters or maybe even filaments and even larger structures? Is it the same, or are there different processes contributing to the magnetic field? How it is related to large-scale structure? Is there a difference between this galaxy cluster which shows this cool core or this galaxy cluster which shows merging? So is it related to the turbulence, or does these processes give some imprint on the intrinsic length scale? Is the magnetic field just a magnetic field, or it has a power spectrum distribution and things like that? And again, observables we have at hand are rotation measurement in clusters and radio emission. Now, rotation measurement, as I already said before, what you need is you need some source of polarized radio emission in the first place. In the best case, something very far away in the background so that it doesn't interfere with your object. And that radio emission is propagating through the large-scale structure. And then if it propagates through a galaxy cluster, it undergoes Faraday rotation, which means that depending on its wavelengths, the polarization vector is rotated, and you observe it at various frequencies, and you can reconstruct the so-called rotation measurement, which is directly proportional to a line-of-sight integral of the electron density and the magnetic field along the line of sight. So here are two examples of two sources inside galaxy clusters. So these are two radio lobes of AGNs. And again, the shape is just given by the screen which is produced. So that has nothing to do with the magnetic field. It's just your observational window. But the color code on top of this map is reflecting the rotation measurement. And you can see already here that it has a quite distinguished structure, and it's not a kind of simple model. So roughly 20 years ago, the situation was like that. There have been of order 10 of these sources observed. There were something like 100 collection of 100 point sources behind clusters where you can try to do some statistics. And what you do is usually you did a very simplified model. You said, okay, you have a typical magnetic field and you have a typical length scale, and try to figure out what best of these two values will fit these observations. And typically you get something like order microgauss with very large errors, and length scale which are tens of kiloparsec, again, within a very wide range. Now, after that, more and more observations came up, and I will show you a lot of these observations in detail because you can learn a lot of things from that. And these observations then help to develop more and more a more common model, and to see what is the distribution of magnetic field spatially and energetically, so power law distribution of the magnetic field power and radial declining magnetic field and things like that. And then when you want to interpret radio observations, you have to face the problem that how to get the cosmic rays. And here's the challenge, is that, so what is plotted here is the energy of relativistic particles inside a galaxy cluster, and that is its lifetime, so to speak, its cooling time, how fast it loses its energy. And to have radio observations, you need electrons which are in that region here, which are synchrotron bright, but they cool extremely fast. Now, in the case of radio halos, you have to distribute these things over megaparsec scales, but they have such short cooling time. which means that you cannot just produce it at one place and then distribute it, because the time it takes to distribute the stuff is much longer than it takes to cool away. So you have to find a process which allows you to accelerate or to produce particles, relativistic electrons, over this very large region. And there are basically two common models to do that. One is you can start with cosmic ray protons. They have much longer cooling times. So basically, they stay in the galaxy cluster. They cannot escape. They stay inside, but they almost don't cool. So once you have ejected cosmic ray protons by AGNs or by whatever, they stay in the cluster, but they can interact hadronically with the thermal gas, producing pions, and they decay then in cosmic ray electrons, so that if you distribute these protons in the cluster, you have a source to produce relativistic electrons at very large volume, but you pay the price that in this process you also produce gamma rays. So if you observe gamma rays, you can also get some limits on this kind of process. Another process which is discussed, which is much more difficult and therefore is not so much discussed, although it nowadays looks like it's the process which is better suited, is that given you have this cooled down electrons, you can reaccelerate them by MHD waves driven by the turbulence. That's a very complicated process, very difficult to model, so it's very difficult to make models, but that also would allow you to produce cluster-wide some relativistic electrons here in this region where you need them to emit. Oh, yes, magnetic reconnection. So, yes, but I think the process is not efficient enough in clusters to accelerate. But sometimes it's discussed. But so far the kind of interpretation is that at least within this megaparsec volume, reconnection will not take place in that way where you need to produce this. So, and to study all that, you start to get an increased number of complexity in observations. So you can look at spectral index maps and see if you can nail down from the spectral distribution of the observed radio emission what is the acceleration process. And you get some information now. Also, as you saw from the maps, some are good enough to make some radial distribution, so you know how the radial surface brightness should go. And again, all these processes can give you some handle on what is the most likely process going on to create this radio emission. And also now we start to get some samples which are large enough to do some statistics, so to answer detailed questions like how probable is it that a galaxy cluster shows some radio emission. So again, here, kind of the last summary slide here. Again, here's this map of all the radio halos you saw. When you look at them, if a galaxy cluster shows a radio halo, then you usually find a strong correlation between the overall properties of the galaxy cluster, like its X-ray luminosity, its temperature, its mass. You can plug in whatever you want here, and its radio luminosity. And all these clusters which you observe always form a quite nice correlation. But then there are galaxy clusters where now we have upper limits which don't show radio emission at all. And again, that is a kind of challenging for these models. And so now you're left with this kind of zoo of models where for the peripheral you have to understand shocks and the acceleration in shocks. And for the central sources you have to understand either turbulent acceleration or hadronic models and things like that. So, to wake you up again from this kind of overview, here's a promised slide on what chaos and magnetic fields have in common. So there was a very nice article by Begal et al. In 2008. And what they did is they used Google Maps. So Google Maps indeed has also scientific interesting things. And what they measured is they looked at maps and they searched chaos. So you can on these maps identify cows, and if they are in a herd, you can measure what is the mean direction the herd is pointing. And they made some statistic from that. And they did not only use Google Maps with cows, but they also looked for deers and for bears in experiments where they went to the woods and checked the directions. And when they plot the diagrams here for the different animals, you see that there's a clear direction where they usually point, and they make some cross-checks that it's not to do with shadowing or with the sun direction. And the funny thing is that here's pointed north-south geographically, and this real direction the animals have is along the magnetic north-south. So if you look at the magnetic poles, it's exactly that direction. So they claim that cows still have some sense of magnetic fields and other animals, and cautiously, when they are at rest, they use that to navigate to point in a certain direction so that if there's some danger, they can escape in the correct direction, so to speak. So that was a kind of very interesting paper, and again, it's quite nice to see that magnetic fields is also interesting for animals, and of course we know that for the orientation of birds when they move, they use magnetic fields and things, but there's even more out there, so even standard cows know something about magnetic fields. So back to magnetic fields in galaxy clusters. So as I said, Faraday rotation measurement gives you a tool to measure this kind of extended maps, to investigate these structures, and to do so, you can do either very simple interpretation, you can try to do a direct inversion, which is quite complicated, and so it's not many attempts in literature to do that, or you do some modeling, where you set up a synthetic model, produce your artificial observables, and compare to your real observation and constrain model parameters. And that is actually the technique which is nowadays mostly used. In the very early days, as I said, you have had samples of point sources where you could plot the rotation measurement as function of distance to the cluster sample, and that are two different works with two different samples. And what you can see is that there's a clear sign that the dispersion of the rotation measurement increases if you go towards the galaxy cluster center. So that's a clear sign that there are magnetic fields in galaxy clusters. And it also, if you investigate the samples, it looks like that all clusters have magnetic fields. So it's not that some clusters here don't show any signal at all. So it means that magnetic field seems to be a very common feature in galaxy clusters. You can do other tests. Instead of measuring the rotation measurement, you can ask, suppose I don't resolve my source because it's a point source, so I get it observed within a beam. So which means that within the beam, the different magnetic fields I have in the front and the different orientation will cancellate the signal, and they will even lead to this beam depolarization. So you can measure the amount of polarization of the sources, and that's a work from Bonafede et al. Just very recently. They took a sample of very bright X-ray clusters. They went to the archive. They looked for all radio point sources which are in a certain distance of the galaxy cluster and measured the polarization signal. And then you can plot the fractional polarization as function of distance, and again you get this very nice signal that if a source is passing through the central part of the galaxy cluster, it gets more depolarized than if it has a larger impact parameter. And again, you can do some kind of very simplistic models here where you vary the parameter, and overall the result is that you find a mean magnetic field which best reproduces the observational data. And you can then try to use this statistic set to make two groups of galaxy clusters, like merging, non-merging, hot and cold clusters, and they tried all that things. They didn't find any significant difference. The only significant difference in galaxy clusters they found were when they divided the sample in cool cores and non-cool cores. So it indeed looks like that in a cool core cluster where you have this high density, you have also larger magnetic fields. Movie will show up. So now, if you want to interpret this magnetic field in galaxy clusters, again, I want to show you one simulation. So you fly around a simulated galaxy cluster which does not evolve any longer, but there's an AGN plugged in the center, and these radio lobes are driven through this atmosphere. So that's, again, it's just to visually show you what you do when you interpret rotation measurements. You take these lobes, which reflect just the velocity, the shape of these things, reflect how the AGN is propagating, the velocity field of the galaxy cluster, and you take that as a screen and measure all the magnetic field here along your observer direction. And again, as you can see here, that's MHD turbulence, so it's not just a random field, it has some correlations. Although you describe it maybe as a power law, it's not the same than if you take a power law and build a random realization of that, because you still have some correlation which is visible in this kind of streams and filamentary of the magnetic field. So that is a caution you have to put on. No, for this work, for this work here, it's mainly AGNs in the background, right? And for these also. But if you look at these kind of maps that are usually central maps or radio galaxies embedded inside the cluster, and most of the constraints of the models come from these kind of sources. The other ones are usually just confirmation on the presence of magnetic field or some concepts. But it's much more difficult to get detailed model parameter out of this kind of statistical samples than what I will show you in the next slides, what you can derive from this kind of radio sources. And that, again, is just to emphasize what you're doing is you have this kind of shape which is given by the AGN, and you look through the projection of the magnetic field towards that, and then you try to infer properties of this kind of magnetic field, making simple assumptions, which, as you can see, might be not the best thing you can do, but still it's what you can do at the moment. So that is one of the rare attempts to do even an inversion approach to that. So you take this rotation measurement map and you take a model of the galaxy cluster, so you observe it in X-rays, so you get an idea on the temperature distribution and on the density distribution. And then you can ask, what kind of magnetic field do I need to reproduce the observations? And what you can construct is what kind of magnetic field you have to plug in, which are these lines. So that is a power spectrum of the magnetic field as function of the wavelength. And you can ask, what do I have to plug in here to measure this, to get back this map? And that's work by Vogt and Enslin, and there's a newer version of that from 2009, where it's even extended to larger and larger scales, so to smaller and smaller k. And what this work is indicating is that, indeed, you obtain a kind of Kolmogorov-like spectrum, which the magnetic field has to have to get this to get this kind of Faraday rotation maps. Now, sometimes you are lucky, and you have these galaxy clusters where you don't have just a central source, but that, for example, is ABL 114, and here you have three sources where you can use it to map rotation measurement. And again, here are the rotation measurement maps of these three sources. So what you now can do is you can, first of all, of course, try to measure magnetic field or model magnetic field to reduce the source properties. So that gives you information on length scales which are of order the source. But then you have also three different line of sights through the cluster, which might help you to constrain the magnetic field distribution in the cluster, or even the magnetic field power spectrum on larger scales. So for that, again, you do a very simple approach. You model your galaxy cluster from the X-rays. So again, the contours here are the surface brightness from X-rays. You can obtain temperature and density distribution from that. And then you can set up a magnetic field where you say, I take a very simple model. I take a power law distribution of magnetic field fluctuations with different spectral index. Then I make synthetic maps. And you can see that depending on the shape of the power spectrum, you get these different fluctuations in the rotation measurement. You can then ask some question like, what is the predicted rotation measurement dispersion, for example, as function of the distance, or the predicted mean rotation measurement as function of distance. And you can plug in these different models with either different central magnetic field or with different power law, and you can try different model parameter and see which one fits best. And you come up with, in that case, that a spectral index of -2 here gives the best fit with length scales varying between something like 6-ish and several hundreds. And if you, for example, want to fit a Kolmogorov spectrum with that, you have really to limit your maximum length scale to a certain range. So that is already telling you that some of these parameters here are, of course, degenerated. So you have to try to break these degeneracies. And again, that's just a visual impression. So that is the observed rotation measurement pattern, and that are here the rotation measurement patterns for different models. You can even calculate some structure function of these things. And again, if you do that, you find that if you look at the structure function, then spectral index here of -2 instead of Kolmogorov is preferred for that cluster. But again, question is, can we include more observables to constrain this kind of models better? So that's another case. That's Abel 2255, again a galaxy cluster. The color map here is again X-rays, so you get temperature and density distribution. And here in that case, you have 4 sources located inside the galaxy cluster. You can do the same kind of game, but now you can also, as this cluster also shows a diffuse radio emission, you can ask, how would the polarization of that radio emission looks like? And again, you can make different spectral index for the magnetic field, and you can ask how the synthetic polarization maps would look like, and you can compare that to observations. And if you do that with this kind of galaxy cluster, you find even that one universal slope of the magnetic field power spectrum doesn't work. So you have to vary it as function of distance. Again, either that's a kind of very interesting hint towards very complex dynamics in these systems, or it's just a reflection of that this modeling is still not 100% perfect. But again, it shows you that combining these kind of different observables give you more and more power on constraining the magnetic field, and of course, future instruments will be here really fabulous in making models and constraining. And again, the impression you hopefully take with that is that really, if you look at these works, is that it's really a growing field, and we expect a lot from all these new instruments which are partially already operating or will go into operation, hopefully, in future. Now again, we are now in the situation that we have several of these sources, and we can try to do first kind of statistics. So what is plotted here is the dispersion of the rotation measurement as function of distance, now for all these elongated sources for various different clusters. And they are all plotted here. So again, you see the clear signal towards the cluster center. But the nice thing is now if you even distinguish the temperature of these different systems and color code them, you can clearly see that the high temperature cluster lead to a much larger signals than the low temperature clusters. So the question is, can we already infer some interesting scaling of the magnetic field with temperature from these kind of experiments? And what you, for example, can do, because the rotation measurement is not only proportional to the magnetic field, but also to the density along the line of sight, you can try to do a somewhat different plot. So what you plot here is the X-ray surface brightness versus the rotation measurement. And what that means is that this X-ray surface brightness here is proportional to the square of the density, whereas that signal is proportional to the density times magnetic field. So in a very simplistic interpretation, the slope here of that correlation tells you how magnetic field is scaling with density. And then you can even look if there's indication if hotter objects have different normalization of these correlations than low temperature cluster. And again, unfortunately, the data and the errors on the data are still too large to say some clear results. I think there is a small indication that red points, for example, are above the blue points, but again, the errors in current data is not good enough to really do some clear investigations on that. But again, future instruments will help. So there are even some more spectacular examples, and again we are back to our Coma galaxy cluster, which is a very famous galaxy cluster. It's close by, so very well observed. So in that case, we have even 7 of the sources inside the cluster. So you have 7 different lines of sight you can probe. And again, what you can now start to do is you model a magnetic field as following the density, as we saw from the previous plot. You model the magnetic field power spectrum as a power law. And then you even start to plug in minimum and maximum scales and see if you can constrain this kind of parameter of a simple model much better. Again, what you can do to measure the models against the observations is you can define some structure functions as done here, either with the sign of the RM or without the sign of the RM. And you can again have the dispersion of the rotation measurement as function of distance and its absolute value. And here are some comparison between the data, which are the red points, and the models, which are the different color lines. And you can see how different models are reproducing the different observables in different ways. And again, so here you can see how different length scales are modeling that for a Kolmogorov, and before it was for n equal 2, just to see the difference. And then you can, with this kind of high quality data, you can do even kind of constraining maps where you plot some parameters like this, how magnetic field is following the density versus the central magnetic field, and you can explore your model and you get some sigma contours on what is the best, so you can constrain some values. If you, for example, look at the shape of the power spectrum and the maximum correlation length, you can see that, as you saw before, there are some degeneracies, so you get models which are best fitting along the line of sight. So as long as you don't have any further clue on either the maximum length scale or the slope of the magnetic field power spectrum, you cannot distinguish models very well. But at least some of the parameters like central magnetic field and the following with the density are quite nicely constrained. Now, again, as before, you can include radio emission and polarization of the radio emission, because that is very sensitive to the large scale part of the magnetic field. And again, if you, for example, take this cluster Abel 655, where you have several observations, plus you have a radio emission, a radio halo, you can infer an outer scale of several hundreds of kiloparsec. And also, if you look at depolarization, then there are first hints that this power spectrum also has to be limited to small magnetic fields. So there has to be a scale below which the magnetic field cannot continue to be structured like a larger scale. Now, that is very interesting, and there are several papers now which try to investigate that in more detail. And again, that is one galaxy cluster. Here in red is the X-ray observations. You see the radio lobes, the sources here. You see rotation measurements here. And people now start for investigate that to improve even the modeling of the thermal part. So instead of using a simple distribution of the electron density, say here to account perfectly for the cool core, they do a double power law, double beta model to get a very exact distribution of the densities. You even start to model these cavities, which you saw before, because also that is influencing your results. So to speak, you get a very, very detailed model on how the densities are distributed. And then you use rotation measurement and depolarization analysis as before. And what you can do is now, again, constrain this kind of models much better. Again, here is the observed quantity at different frequencies of the depolarization in that case, and that are the model quantities for different models you plug in. And now you can, again, explore all the parameter space as done here. So you can plot different parameters like spectral index versus maximum length scale or minimum length scale versus polarization against. And then you marginalize over the other parameters and you collapse these contours to distributions, so you can give these values with, say, according error bars. And again, you find tens of microgauss in the center, which is quite good value. Spectral index of 2.8, which is going more close to Kolmogorov. Something which follows the density. But again, the most important thing here, which I want to stress, is that again you get strong indications that below, say, half a kiloparsec or so, the magnetic field structure has to change, and you cannot continue at that slope. Otherwise, you would get too much depolarization. You wouldn't be able to observe the signal. And again, here, for example, that is the radial profile of the depolarization here with the data points on top. So that is a very strong indication. Now, going back to the magnetic chaos, as we now did also in the cluster, we can make more and more detailed models. So you can also make more and more detailed models for your magnetic chaos. And there was a very interesting paper again from the same group, but that time led by a student. What they did is they went back to their maps with the chaos and said, can we measure first moments on that distribution? So is it really always north, or can we disturb the chaos? And what they did is they looked in Google Maps also for power lines. So because this power line will induce a magnetic field, it's a low-frequency magnetic field, so it will disturb the Earth's magnetic field. And you can make a model on, if you are at a certain distance of the power line, how this superposed magnetic field will be looked like. And you can distinguish the case where the power line is going along the Earth's magnetic field and it's going perpendicular to the Earth's magnetic field. And if you do so, and you group your pictures in that way, you would predict that if you are close to, you would be disaligned, and as you go further away, you're more and more aligned. And if it's orthogonal to the Earth's magnetic field, you would say the distribution of the direction of the chaos should be following this kind of pattern, and only if you're far away, you again follow the north-south pattern. And now you can look in your data how that looks like, and you have to compare this first row to that row, and again, there's at least some indications that, here you might have this kind of rotating towards, like you would expect here, and here you have this kind of four peaks changing to this kind of collapse on the line. Yes. And then here's a group that they select all the cows which are relatively close to power lines, and then they do the two groups where power line. Usually it's a couple of hundreds meters, and you have this herd of cows, and you, so to speak, measure the individual direction of every cow, and you build the average for the full herd. And that is what you use in these diagrams. So again, just as an indication, magnetic fields, if you look in the details, can be quite surprising. So, back to our galaxy clusters. So, as I said, if you look into diffuse emission, then you have these two phenomena. One is this radio relics, and again, here's an example of this cluster, and in red is the thermal gas, so you see here the galaxy cluster, and in blue is the radio emission, so you see the two relics here in the periphery, which are not related morphologically, not directly related to the underlying gas, but still you see that it's related to a merger. Typically, these sources are highly polarized, and they are, as I said, in the peripheral region. If you look at radio halos, again, here red is the cluster gas, and blue is the radio emission, and you can see that morphology, they are much tighter connected. They're usually not polarized at all, and again, they have the kind of same length scale. Now, how do you come to this kind of models? As I said, these relics usually are related to shock waves, and these shock waves will, on one hand, accelerate electrons, and here the big question is, what is the efficiency, how is air related to the Mach number? But they will also compress the magnetic field, so you get slight magnetic field amplification, and they will orient the magnetic field. So that might be the reason why you see this huge, large polarization, because inside the shock, the magnetic field will be all aligned. Whereas for radio halos, this merging process develops turbulence, and it might reaccelerate the particles, which means that merging is really a need for this phenomena, but not every merging cluster shows radio emission, so there might be a time delay or a lag. And there's a second possibility that you can go via hadronic interaction, so you have cosmic ray protons, which interact with the ICM, and the decay process gives you relativistic electrons, also distributed over relatively large scale. Now, what can we learn from these kind of observations? So, again, there are two nice pictures of radio relics. Again, you see the X-ray contours and the radio relics outside. Again, here in color, you see the X-ray, so the thermal gas distribution, and the relics outside. And the interesting thing is that if the electrons get accelerated in front of the shocks, they will cool. And the cooling time of the electrons, of course, depends on the magnetic field. So the width of that region here, you can see, gives you an indication on magnetic field strength. And again, what you find is, for this kind of early work here, it's that you have typically microgauss in this kind of structures. And again, here's a collection of different morphologies. So sometimes, like here, you have thermal gas and you have only one relic. In some cases, you find this double relics. Some cases look very spectacular. It's more ring-like shape, so it's very difficult to understand how that comes into place. Again, here that's a typical double relic. And that thing here, again, has a very strange shape, which is not this kind of classical bow shock like you see in other relics. So there might be even subclasses which you have to distinguish a little bit more careful. Now, if you look at these relics at different radio frequency, you can make the spectral index of the radio emission. And the spectral index is found, if you look at the sources, to change along the relic. So in front of the relic, where the particle acceleration is happening, it should be related to the Mach number. So you can get an indication of what kind of Mach numbers the shock has from this radio spectral index. And typical Mach numbers are between 2 and 4. And again, that's quite interesting, because the range on which, in principle, we think that cosmic rays can be accelerated by shocks is more or less in that range. So if the Mach number is really only 2, it's very difficult to understand, because at 2 you would expect that cosmic rays are not accelerated. If it's 4, it's usually no problem. So again, detailed understanding of these things will lead to very interesting insights on this acceleration mechanism. And again, that's again double relic here, where you see again the change of the spectral index, again, which means that the electrons are cooling behind, and you can get some information on magnetic fields on that. That is just recent MHD simulation by Skillman, where they even trace the Mach numbers in their simulation, and they try to see what kind of relics you get. And if you, again, compute this kind of spectral index maps from their relics, it looks like that you can reproduce these things quite nicely. So indeed, there are more and more indications that these things really fit together. That's another interesting work by Franco Vazza. Here. I put it here. But now the interesting question is, what is the probability of this relic to be found at a certain distance? Because observational, as you saw in all the examples, we find the relics preferentially at a certain distance of the cluster. So if it's too close, maybe the shock is not yet strong enough to accelerate particles. If it's too far away, the magnetic field might be too small, but it's something which really has to be investigated in detail. And one attempt is done here. So that is the number of relics as function of distance to the cluster center, and there's a compilation of all the observations, which is this dashed black line here. And then there are these different lines from models, either based on simulations, just taking pure geometrical effects, or then just try to model different properties like the magnetic field distribution, the efficiency of the acceleration mechanisms, and so on. And if you then take these kind of simulations, you get the statistics of the shocks which are predicted by the simulations, and you ask how many relics you would expect, you find these colored lines. And you can see that on first glance, you get a kind of similar distribution, but if you look in detail, it's quite difficult to reproduce the exact distribution, which again points towards that we have to understand more clearly the detailed mechanism how these relics are produced. Now, again, that's a very nice example of a relic, which is, by the way, called sausage relics by the Germans, because it looks really like a sausage. Again, the interesting effect here is that you solve this relic to be very thin. You see the spectral index map, so you see the acceleration and the cooling, and then you can make, again, some modeling on how big the width you would expect inside the relic, depending on the magnetic field, and that is some kind of very simple model here. And again, you can take the size of the relic, and you can see that this model has basically two solutions. Either magnetic field is of order microgauss, or it's significantly larger. It's even 5 to 6 microgauss here. And the thing is that if it's only 1 microgauss, it's very difficult to produce the total luminosity of that object, because you would need much more cosmic rays. So basically, the authors argue that in principle it should be the larger value, because then you make the model more complete and also the total luminosity. However, to have 5 or 6 microgauss in that relic at that distance of the galaxy cluster is again quite a tough thing. So again, this kind of observations are really showing things which are very difficult to explain. You have to do detailed modeling, and at the end, when you have more of these examples, you will learn a lot more on the magnetic fields. But so far, we have a couple of good examples, as I showed here, and it's showing very interesting results. But again, it's very difficult to make a fully complete model which explains everything from first principle. Now, what can we learn from this radio halos? So as I said, if you look at this huge volume emitting in radio, where you need some magnetic field and cosmic rays, can you constrain magnetic fields, or at least the acceleration mechanism of the cosmic rays in these kind of models? Here's one attempt to check how that would look like with simulations. So that is 2 galaxy clusters simulated, so where you have a X-ray map, temperature map, and a predicted radio map, because that were MHD simulations, where you just assume a very simple model for the secondary emission. So you assume a simple model how the cosmic ray protons are distributed in the galaxy cluster. You let them interact with the ICMs. They produce your secondary electrons, and they then, within the magnetic field, produce the radio emission. Now, if you do this kind of simple models, what is nice that they automatically can explain this kind of very nice scaling relation between radio halos. So in that case, we just plugged in that the cosmic ray protons are a certain fraction of the terminal protons, and you get this kind of nice correlations. But again, you see already that it's difficult to explain these non-detections, because with these kind of models, all clusters should show radio emission. And again, there are strong indications that there are many clusters which don't show radio emission. So these kind of simple models fail to produce probability. Now, if you look at the evolutionary track of a single cluster, again, in the same diagram. So here you see, again, how a single cluster is evolving. So when it's merging, it's going up the correlation, and it relaxes in going down. But again, the main evolutionary track of this kind of clusters is along the correlation, and again, no chance to reach with this cluster this region where you don't see any radio emission. So either you have to build in somehow very strong dissipation of magnetic field, so that after the merger the cluster goes really down here, or you have to find some mechanism of transport the cosmic rays out of the cluster. And both are discussed in literature, but they are not very successful yet, I would say. Now, another problem with these models is if you look at the size over which the radio emission is coming, as in the secondary process, your cosmic ray electrons coming from a process which cosmic rays are scattering with the thermal protons, you have some n square term here. So if you go further out in the cluster, you have less thermal protons and less cosmic ray protons. So you get even less cosmic ray electrons, and the emission is dropping out much faster. And you see that, for example, if you plot the typical size of a radio halos versus the size of the galaxy cluster, you have the observations up here. And if you do the simple models I showed you, you will end up down here. So you will produce the emission in a much too concentrated region. So also you produce the total luminosity, you fail to produce the large extent. You can model that even in more detail if you take a model of the Coma galaxy cluster, which was done here. So again, that's an MHD simulation, so you get a magnetic field. You can compare that magnetic field with observations. As I showed before, it more or less fits. And then you can ask what kind of cosmic ray proton distribution you have to plug in to reproduce the radial distribution of the radio emission, as here the green histograms. And you can see that you have to fit with the light blue line, you have to put a lot of cosmic ray protons in. So at a certain distance, you have to have as many cosmic ray protons as you have thermal protons. And again, that is a very strong disfavor of the model. And there are now even limits on the gamma rays this kind of process will produce, which are overshooting observed values by a large amount. So this kind of model, also simple and produce some basic properties, it has many problems in details. And again, one of the largest problems faced by these models is that if you look at the radio spectrum of, for example, again, Coma, so the radio halo observed in various different frequencies, represented here by the black dots, you see that that spectrum is curved. So if you have a secondary model where you scatter relativistic protons with thermal protons, you would expect a pure power law, which is the dashed line here. And then you might even discuss if some effect of the so-called Seldovich, which is a decrement of the CMB background, as that frequency might contribute a little bit. So that is the red solid line. But still, you're not able to match the real observed spectrum. And this curvature, again, is a strong indication that there has to be some kind of more direct mechanism to accelerate the particle, because this curved spectrum is a clear sign of cooling. So you have to have a process which is dominated by the cooling and not a steady state which comes from scattering of higher energy particles. Now, again, in summary, given that this kind of very simplified models are disfavored in various aspects, you can think about what turbulent acceleration could do. And there's a lot of literature on theoretical part on that, but I just want to show you one example where one puts that into even a cosmological simulation, and also should show you why it is so complicated and why no one is doing that in practice so far. Is because if you want now to solve this turbulent real acceleration, you have to follow the relativistic electron distribution function. So meaning that you have to have a distribution function, and you integrate this distribution function for the loss terms, for the cooling, for the diffusion terms, and of course for the source terms like the turbulence you measure to accelerate. So you have a distribution function which you now have to solve for every volume element of your simulation or for every particle in the simulation. And that is of course quite costly. Then you can assume some acceleration term, which is linked to the turbulent velocity, which you can take from your simulation. And you can put in some seed electrons, because this kind of turbulent acceleration cannot accelerate electrons directly from the thermal pool, so you need some mildly relativistic particles to accelerate. And if you do so, that is one of the first simulations of that kind, where you have a galaxy cluster merger here. You see the density, so here you see how the shock is formed, the temperature is evolving, and that is how a radio emission would look like. So you see that at the beginning you have very low radio emissions, then you pop up a halo and it dies out. That's exactly this process of that doing this merging. Turbulence is built up, you accelerate your electron population. You build up halo and it dies out again. That's again a more detailed look at the halo. And again, you see that, for example, the solver has also problems at the beginning with the shock, so you have to switch off the shock here, otherwise the solver gets a little bit confused. But for the general turbulent acceleration, it looks quite nicely. Oops. You can now look at the spectrum you expect from the radio emission of such kind of process. And again, the black points here are from the Coma, as before, now just again multiplied with the frequency to have it nicely to display. And you can look how the radio spectrum looks at the beginning. Then the merger happens. You get a very nice spectrum after 1.6 gigayears of the merger. So you have had enough time to build up the turbulence, to do the reacceleration. And afterwards, it dies out again. And you get a very steep spectrum, which is just dominated by the cooling losses. You can look how that looks in a luminosity temperature plane again. So here are all the scaling, all these asterisks and diamonds are the observed radio halos. You start here with your system, it evolves up during the merger, it goes back to the correlation, and then it dies off when the radio goes up. So that's this kind of process for the first time can demonstrate that you can have this kind of radio quiet clusters here in the zone where you have the upper limits. By the merging, it evolves up to the correlation, and then it dies out again. So, is that all? And again, to answer that questions, I want to come back to my lovely magnetic cows, just to put you a warning. You saw all these nice results from the cows, right? But then if you look in detail, there are then papers which claim that this cow alignment is not true. Then there might be some answers of the authors which show that it's true, and they're discussing statistical processes needed to measure these things and things like that. And then there's another author's response on that also these corrections the original authors do is wrong, and so on. So that's just a warning that we do our best, we look at things, we think we understand things, but better to check, and in science it's always a discussion. So all the results I have shown, please take them with some sort of grain. They are simplified models. We try to learn something, but there's always the possibility that someone is overinterpreting some stuff. And even worse, it might even depend on your environment, because, for example, if you look in more detail, what happens to cows and magnets, if you're in the US and you're a farmer, you feed your cows with magnets, and you might wonder why you would feed a cow with a magnet. And the reason is that when they do their grazing outside, there's a lot of metal debris, and many cows usually die when they eat this metal debris because they are hurting them inside. So they get this cow magnet, feed it, and it stays in the stomach, and if the cow is eating this metal, it sticks to the magnet, and the cow is surviving. So again, that might even influence your measurement in principle. So just as a sort of grain, be careful and check your environment. Okay, so final conclusions. What we learned from rotation measurement is that it looks like magnetic fields in galaxy cluster has a power law-like distribution. Kolmogorov seems to be a valid solution. There are discussions on the exact spectral shape, but as well as direct inversion of the maps, as well as indirect modeling, suggests that at least Kolmogorov seems to be a valid model. There are indications of a lower cutoff in magnetic field strength, length scale, And of course, there's an largest scale which is involved. And again, more detailed measurement of these two scales are really important because the larger scale, of course, tells you about something about injection. So which kind of merger process is driving the most of the magnetic field. And the small scale, of course, tells you something about plasma processes, at which point viscosity is important, at which point transport coefficients get important, and reconnection is happening and things like that. And if you look at simulations, that's just, again, one example, and I tried to plug the simulation correctly inside the length scale. So simulations are, as you see, still far away from reaching this kind of lower scale in predicting power, but on the large scale it seems to be fine. So this kind of peak, which we would interpret as injection scale, is roughly where the observers are claiming that the peak is. So overall, we are on a good way, but there's a lot of way left here for people who want to do simulations, and there's of course a lot of stuff you can do here as observations. And as I said, instruments are going online and are coming, which provide even much better data than we have at hand now. And from diffuse radio emission, again, we have two classes or two main classes of emissions. One is this peripheral emission, which is related more or less directly to shocks driven by mergers. And there's this diffuse central emission, which is also related to merger, but with some different mechanism, like turbulent reacceleration, most likely, or any of this kind of process. In this external thing, we can measure polarization and size, and that gives you some good indications on the distribution of the magnetic field and the strength. And you can measure the spectral index of the radio emission, which gives you some indications on the Mach number and on the acceleration process. Whereas in the radio halos, you have some more global scaling relations like size or radio power or probability to host a radio halo, which is constraining again your emission model. And I didn't make a break in between because I thought it might be better to go through, and so we have now a much longer coffee break to discuss things. So, and I'm happy if you come for questions, or you can of course ask now or during coffee or any time come and ask questions. Well, so far people mostly discuss direct acceleration at the shock. So this merger, as you saw in the movies and also saw in the observation, has two aspects. It drives this bow shock, which is going through the whole cluster. Basically, if you ask where the cluster is getting its temperature, it's these kind of shocks which are defining the temperature of the cluster. And then when it runs outwards, the Mach number increases because you run in lower and lower density material. And at a certain point, it looks like that acceleration gets efficient enough so that you get this kind of peripheral emission, which is called radiohelic. So far, people discuss direct acceleration by shocks, like Fermi 1, right? But if you look then in detail for the Mach numbers, for some of this, you can, for example, in X-ray observations, try to get a Mach number, and they are typically slightly lower than what you would infer from radio. And again, in this regime of 2 to 4, it's quite interesting because if you look at theoretical models of where people try to do that in direct simulations, how particles get accelerated, they typically find that around 2.5, there's a break. So below 2.5, they don't get particle acceleration, right? And above 2.5, they get, but it's still very inefficient. And only if you go to 5, 6, then you're very efficient. But you are exactly in this regime. So there are serious doubts that it might be more than just direct shock acceleration, that there might be some plasma instabilities behind the shock, which then do either turbulent reacceleration or maybe even by reconnection in this case. But it's so complex that people really, it's very difficult to model and to find good arguments to describe things. So, and this shock, so to speak, in the first part, if it's only mildly accelerating, might, so to speak, produce the seeds, which are then later re-accelerated by the turbulence when the cluster core is really relaxing and dissipating all its energy. Another thing which is, and I wanted to discuss that in the third lecture a little bit on when it's about modeling, what people are thinking of. If you have these radio lobes, these old radio lobes, where you have this kind of already very much cooled down electrons and protons, but they rise buoyancy, and you see this kind of bubbles already at relatively large distance. So you can think about a shock hitting this kind of structure and then re-accelerating. And there are some of these observations, like this one ring-like thing. That is some structure which you would expect from this kind of process. So it might be indeed that there are even different processes which we now still call all relics, but some of the relics are really direct shock, others are compression of fossil radioplasma. So it's just that the statistics at the moment, you have something like 10s, 20s of objects, so it's very difficult to do a fair statistic. Sorry? Yeah. Let me see. You mean here? That's not really known. So what people discussed is, for example, if some of this emission which you see more in central, if that could be this kind of relic, just think on an umbrella-like structure, seen from top, for example. But then you can do statistic, and it doesn't look like that. This diffuse emission here in the center you see can be explained as a relic just seen face on. And also, it's very common that they are very, very thin and very elongated. So it really seems like, as they have so low surface brightness, you really need to have the shock almost in the plane of the sky. Otherwise, you can't detect them. If they are a little bit tilted, then it gets already difficult to detect. And again, people are using simulations to test this kind of geometrical effects. It's interesting to do so, but again, you have to be a little bit cautious, because also in simulation you have the kind of uncertainties on how you detect the shocks and things like that. I will show something in other lectures. The problem is, I will discuss in the lectures what the cluster tells us about the seed of the magnetic field, how simulations, different kinds of simulation to produce these various aspects of that. But for the dynamics, it's a problem that you have the sound velocity, which is that thing. Typically, observation is showing that turbulence is order 10%. So turbulence still plays dynamically some role. But usually magnetic fields, if you take these values you obtain from the observations, are even not in full equipartition with the turbulence. Say even below that. From the cosmic ray pressure, from the magnetic field pressure sense, they don't play a role. Yeah, 1, 2, 3, something like that. Yes, but 10 is usually in this cool core. So if you look at so to speak, a very massive cluster like the Coma cluster, we have a lot of turbulence in the radio halo. There the central magnetic field is order 4 microgauss. But if you look in the cool core clusters, you get usually in the central of the core, you get some 10 up to 20 microgauss, depending on the system. So there might be indeed that in this very central region of the cool core, magnetic field might start to get dynamically important. But that's something people haven't yet looked very careful into that. Okay.